Hello, everybody. Good evening. Thanks for joining with us. Today it's our 261 International Physics webinar, and we have with us here today Dr. Jeff Murugan, sir, Professor of Mathematical Physics, Deputy Dean, Faculty of Science, the Laboratory of Quantum Gravity and Strings, Department of Mathematics and Applied Mathematics, University of Cape Town, South Africa. He has already connected with us. Sir, good afternoon and good evening to here. Thanks for joining with us, sir. So
Thank you very much. Thank you for the invitation.
It's my honor, sir. So I think our student and viewers can join with us using link. I will send the link in the comment section, and I think they can ask question by commenting in Facebook and YouTube. So I think you will enjoy this session, and the title of this session is A Four-Dimensional Duality Web. I think you will enjoy it. So, sir, it's your time. You can start your session.
Thank you. Thank you very much. Great. Excellent. So let me see. Great. So I assume everybody can see this. The title slide, is that right?
Yes.
Okay, fantastic. Thank you again for the welcome and for the very kind introduction. I'm not actually the deputy dean anymore, which is an enormous benefit to my time, and I must apologize in advance. My dogs are likely to be barking in the background, but such is life these days, where you're working from home. So I want to talk today about some work that we've been doing for many years now, and it's resulted in the last work, which we call the four-dimensional duality web. And I appreciate that not everybody in the audience is an expert in the topic, and so I've decided to keep it as basic as possible. So I'll start from the beginning, which means I probably won't get to where I want to go to by the end of the talk, but that's fine. I don't mind that, as long as I convey the information that I do convey in an understandable way. So this is largely based on work that I have been doing with a collaborator of mine, Horacio Anastasi, of the IFT in Brazil, in Sao Paulo. And Horacio and I have been working together on this program for many years now. It goes all the way back to about 2014. But I really want to talk about a couple of papers that start off with work that was done in the summer of 2016, the Northern Hemisphere summer of 2016, and then followed up in 2018, and then some work of last year, and there's very much work in progress along various directions that I may talk about a little later. Okay, so let me start off then by talking a little bit about dualities in a very general sense. So it's usually sold as some mystical thing that takes place in high energy physics, and we tend to hold it in great esteem. But it turns out that the idea of dualities actually goes back a long way, all the way to Maxwell's equations. In fact, they're pretty ubiquitous, and they take place in high energy physics, in black holes, in general relativity, and in condensed matter physics. And this is part of the excitement about uncovering these relationships between different theories, because that's all they are. They're relationships between different theories. And what we are going to be talking about today is a very particular class of such relationships. So let me start then by expanding on some famous examples, which I'll start at the simplest form, and then we'll slowly move toward more complicated things. And I'll show you how this ties together in this, what became known as the web of dualities. So our story starts off with electric-magnetic duality. So if you think about Maxwell's equations in a vacuum, these are the statement that if you're in a vacuum, there are no electric fields, there are no magnetic monopoles. If you change the magnetic field, it produces an electric field. If you change an electric field, you produce a magnetic field. So that's the physical content of these four equations. The divergence of the electric field is zero, divergence of the magnetic field is zero. The curl of the electric field is minus the rate of change of the magnetic field, and the curl of the magnetic field is the change of the electric field. Well, the first thing you might notice as a first-year student is that the set of equations is invariant, meaning it stays the same if you make a change of the electric and magnetic fields to the magnetic field and minus the electric field. So that is, everywhere you see an E in those equations, you exchange it with a B. Everywhere you see a B, you exchange it with a minus E, and those equations come out to be exactly the same. So this sounds like a completely trivial observation, and you might be justified in asking, why would you take this seriously? It kind of sounds a little bit like numerology. Well, it turns out that the theory with electric and magnetic field, E and B, and the theory with the magnetic and the electric field, B and minus E, are completely different theories. They're not the same theory where you've just exchanged some symbols. They are completely different theories. And this very prosaic, very obvious sounding fact is actually the precursor to a lot of really deep mathematics and physics. It is the precursor of what we in high energy physics call S-duality. It is the precursor of some remarkable and beautiful geometric ideas that were expanded upon by Witten and Kapustin, called the geometric Langlands dualities. And geometric Langlands builds on the Langlands program to kind of unify all of mathematics. So you can see that these are deep, deep, deep ideas. And they're certainly not trivial. Moving on, a second duality, a second type of duality that you may have heard about is the gauge-gravity duality. And this is the idea largely put forward by Susskind and Toft, that two theories, one a theory of gravity and the other one a theory of matter, gauge theory, are dual to each other. In other words, they encode the same physics in completely different ways. Same physics, same degrees of freedom, reorganized in completely different ways. And probably the most famous example of this is the so-called ADS-CFT correspondence of Malasena's conjecture, that the gauge theory, living on the boundary of the gravity theory, is a conformal field theory. In particular, it's a supersymmetric theory. It's super Yang-Mills theory in 4 dimensions. And this theory is dual to a 5-dimensional theory, the 5-dimensional theory of quantum gravity, string theory in particular, and even more particular, type 2b string theory on anti-de Sitter 5 space, at which, on each point of which lives a 5-sphere. So ADS5 cross S5, the Cartesian product of ADS5 cross S5. Other examples include the Klebanov-Polyakov duality, where the field theory is an ON vector model, and the gravity theory is a theory of higher spins, which is a much more complicated version of the same story, but they're both encoding the same idea, that on the one hand you have a theory of gravity, on the other hand you have a gauge theory, and they encode the same physics. A little more down to earth is the idea of T-duality, or target space duality. And this is a map, a mathematical construction between two nonlinear sigma models. And a sigma model is basically a theory of some set of fields, X, with the metric G, and a two-form field, something like a magnetic field, which we'll call B. And T-duality maps this theory which is a collection of fields XGB, to a dual theory, X tilde, G tilde, and B tilde. Again, different theories completely mapped by this relationship that we call target space duality. And target space duality, T-duality, is one of the cornerstones of our understanding of string theory, for example. But it exists in an even more general sense in field theory. And the fourth example, which is more relevant to this talk, is the idea of bosonization. And bosonization is really just a map between bosonic and fermionic theories. It's not supersymmetric. I'm not saying that there are transformations that exchange bosons and fermions. I'm saying there's a way of rewriting the bosonic theory so that it looks fermionic. And the great canonical example of this is the duality between the massive Turing model and the Sine-Gordon model. Sine-Gordon model is, of course, a nonlinear bosonic field theory, which has a sine phi potential, and the massive Turing model is a four Fermi interacting fermionic theory with a massive fermion. A more trivial example of bosonization is that same map that exists between a free fermion and a free boson with a phi-4 type potential. We'll come back to that in a little bit. So, Pretam, I'm not quite sure how you want me to address questions. Should we leave it for the end?
We can ask question later. So we
Okay.
can add the question in our discussion session, and we can discuss all the question later.
All right, cool. Okay, so even though I've discussed now 4 different types of dualities, they have some common things. So some common points that are worth noting here is, 1, dualities are relationships that typically link one theory at strong coupling to another theory at weak coupling, and vice versa. So where it maps a strong coupling theory to a weak coupling theory, it also maps the weak coupling version of the theory to the strong coupling version. So let me expand on this a little bit and tell you what I mean. So what I mean here is that in a quantum field theory, typically we want to calculate observable quantities because it's a quantum field theory, and observables, as you know from your introduction to quantum mechanics, are the only things we get to calculate in quantum mechanics. Now, when you want to calculate these quantities, the quantities you actually want to calculate, the observables that you actually want to calculate, are correlation functions. And the problem with these correlation functions is that they're typically very, very difficult quantities to calculate. So what you do is effectively Taylor expansions. You calculate it around some value that you know how to calculate around. And whenever you do a Taylor expansion, you need a small number. And that small number is typically provided by the coupling constants in the theory. So you understand the theory perturbatively, meaning you can calculate Taylor expansions at small couplings. But what you learn about the perturbation theory is not all that there is to know about the theory. There's a lot going on at strong couplings. And what these dualities do for you is that they take a theory that's perturbatively well-defined in the one side and map it to somewhere where you don't understand how to do the calculations. Strong coupling. So that's really the power of these dualities. The second point I'd like to note is that many of these dualities, not all of them, in particular gauge-gravity duality, we don't know how to do this, but many of these dualities can be formulated in a path integral language. So this says, I start off with some master integral. Let's call it Z master. And I define Z master as the path integral over some set of fields phi and some other set of fields psi. And it goes like E, it's weighted, this integral is weighted by e to the I times the action that contains phi's and psi's. I don't really care what the phi's are and what the psi's are. They're generic labels if you want. It doesn't really matter. So that's the starting point. That's step 1. Step 2 is if you start off with this master equation, master path integral, and you integrate out, you do the integral over the psi's, then what's left is a theory whose partition function or path integral z, let's call it theory A, is given by the path integral over the remaining fields phi, weighted by this e to the I, let's call it s prime, of phi, only of phi's. I've integrated all the psi's. On the other hand, if I integrate out, starting from the master path integral, if I integrate out the fields phi, I end up with another theory, call that theory B. And this theory is defined through the path integral over the fields psi, weighted by e to the I, let's call it s double prime, which is another action altogether, of just the fields psi. And if I can do that, if these operations are well defined, then I say that theory A and theory B are dual to each other. So this is what I mean when I say I can formulate it in a path integral language. Okay. The next kind of main lesson that I'd like to talk about here is one involving so-called Chern-Simons theory. So Chern-Simons theory is a gauge theory, and by itself, pure Chern-Simons theory has no dynamical degrees of freedom. That means nothing propagates in Chern-Simons theory, and it's a beautiful example of a topological quantum field theory. So everything about this theory is topological. And there's some beautiful mathematics that has to do with knot theory, at Chern-Simons invariance count, etc., etc. And there's also some beautiful physics that has to do with three-dimensional gravity that was expounded on by Witten. But I don't really want to talk about Chern-Simons theory. What I want to talk about is a kind of broken version of it, where I couple the Chern-Simons theory to matter. And when I couple the Chern-Simons theory to matter, it's not a topological field theory anymore. I've given dynamical degrees of freedom. And so it's, in some sense, less beautiful than pure Chern-Simons. But what I want to argue here is that even so, when you couple Chern-Simons to matter, so you're really talking about Chern-Simons matter theory, or Chern-Simons matter theory, the resulting theory is rich and beautiful by itself. And there's some great examples of Chern-Simons matter theories and the richness of the mathematics and physics contained in them. The first example that comes to mind is the so-called Aharoni-Bergman-Jafaris-Maldacena, or ABJM theory, which is a Chern-Simons matter theory that is supposed to be dual to type 2A string theory on ADS4 cross CP3. So CP3 is a complex projective 3-space. It's a 6-dimensional manifold that is fibered into this anti-de Sitter 4 space. And I mentioned earlier that type 2B string theory on ADS5 cross S5 was dual to Yang-Mills theory. So this gave us another, I don't want to say canonical, but it gave us another example, clear, concise, and concrete example of the gauge-gravity duality to study. And for a while, ABJM theory was all the rage, and everybody worked on it for quite a while until they realized that there were deeper things underlying this that we still didn't understand. And this is really how I came into this particular set of ideas. The second point to note, the second example, actually stems from this ABJM theory. And this I'm going to call Aharoni's dualities. And Aharoni's dualities are a set of 3 dualities that connect fermions, so whose actions are the Dirac action, to scalars via Chern-Simons theory. So there are 3 dualities in this list of Aharoni dualities. And the first one says that if I have some number, let's call it NF, of fermions coupled to a UK Chern-Simons theory at level minus n plus nf over 2 minus n plus nf over 2, where this notation of splitting of the level is defined at the bottom of your screen, where um at level k comma l is SUM level K cross U1, comma level ML, modded out by, quotiented out by the discrete group Zn. Those are technicalities you don't have to worry about. The point is that there are three of these dualities. On the left-hand side, some set of fermions coupled to some gauge fields. On the right-hand side, are some set of scalars coupled to some other gauge fields. And the double arrow that joins these two tells me that these theories are dual to each other. So they're really capturing the same physics on both sides of the arrow, but the degrees of freedom are organized in different ways so that they look different. Well, one particular special case of these Harani dualities is if I set everything I can to 1. So in particular, I set the number of fermions to 1, I set the rank of the gauge group to 1, I set the level of the Chern-Simons gauge fields to 1. So NF equals N equals K equals 1. Well, there, the three dualities in the Harani list of dualities collapse down to 2. And they really say the following. They say that a Wilson-Fisher scalar, so Wilson-Fisher scalar is a scalar field theory with a canonical kinetic energy, so d phi squared. And usually it would be a massive theory, so it would have a minus m squared phi squared. And it has a lambda phi to the 4 potential. So, if you're familiar with quantum field theory, this is kind of the first example that everybody studies, right? Phi to the 4 theory with a massive scalar field phi. Except in the Wilson-Fisher theory, you tune the mass of the scalar to 0. So you're at something called the Wilson-Fisher fixed point. And this theory then looks like about half d phi squared minus lambda over 4 factorial phi to the 4. So it has no mass term. It's a massless scalar with a 4 scalar interaction. And the statement here is that this Wilson-Fisher scalar is dual to a single fermion coupled to a abelian gauge field with Chern-Simons kinetic term. I'll come to that in a little bit. Okay. The second statement is that a free fermion, so just a free Dirac fermion, no self-interaction, nothing, is dual to a Wilson-Fisher scalar, again, coupled to a U1 gauge field. So it turns out that, both these statements, actually, this second statement that the free fermion is dual to Wilson-Fisher coupled to a U1 gauge field was already known a long time ago in the literature, mostly in the condensed matter literature. But they're summed up in these Harani dualities in a beautiful way that says that they're actually part of a bigger picture. The fourth point I would like to make here actually ties all of these ideas together, and it goes by the name of Son's conjecture, after Dam Son, who's a wonderful, very clever condensed matter theorist who conjectured that in the field of topological insulators and topological superconductors, that the three-dimensional boundary of a four-dimensional topological insulator, which is a particular class of quantum materials that has remarkable properties that are due essentially to topology and not to dynamics, the three-dimensional boundary of a four-dimensional topological insulator can be described in two ways. The first way is as a gapless, so the energy spectrum doesn't have a gap between the ground state and the excited states, a gapless Dirac fermion coupled to an external gauge field. So you take this Dirac fermion and you put it in an external gauge field, like an external magnetic field, for example, or an external electric field. So that's one description. Gapless Dirac fermion coupled to an external gauge field. The second description is as a composite Dirac fermion. And the composite Dirac fermion is coupled to an external gauge field and a dynamical gauge field. So the external gauge field is something you just take it and you stick this material into this external gauge field. You don't get to control the external gauge field. It's just there. But here, there's a dynamical gauge field as well. And the dynamical gauge field is kind of like an internal gauge field to the theory. The first statement is one of what was called fermionic particle vortex duality. The second statement is what condensed matter theorists or field theorists would call particle vortex duality. And this is the statement that in 2 + 1 dimensions, so physics on the plane, a vortex, and a Nielsen-Olson vortex, like the vortices you find in, for example, a superconductor, actually behaves like a particle. They have the same kind of interaction. So it's very difficult to tell the difference between a vortex and a particle on the plane. And in particular, you can rewrite the vortex theory in such a way that the vortices look like particles in another theory and vice versa. Now, the difference between the particle and the vortex is that the vortex is actually a soliton. It's a very special kind of member of the spectrum of the theory. And particle vortex duality was written down a long time ago by both communities, the high energy physics community as well as the condensed matter community. And it's basically the following statement. It's that if I have some field phi, so this is the last line in this slide, if I have some field phi with a phi-4 interaction and coupled to an external gauge field A, then this is dual to another scalar field, little phi, also with a phi-4 interaction, coupled to an external gauge field, capital B, but gauged. So there's an internal dynamical gauge field, little b. So that's particle vortex duality. It's saying I have two theories. They're both bosonic theories. In the one theory, I have a particular solitonic excitation of the field. In the other theory, that solitonic excitation is interpreted as a particle, and vice versa. The particle in the one theory is the soliton in the other one. The second last line is a statement, is the fermionic version of that statement, that I have a free scalar coupled to in an external magnetic field. So this is I psi bar d slash a, meaning a gauge covariant derivative acting on psi, is dual to another fermion, chi, but this fermion chi is coupled to a dynamical gauge field as well as an external gauge field, capital A and little a. Okay. Okay. Good. So this idea of the fermionic particle vortex duality is something that confused us for a number of years. It was conjectured by Max Metlitsky and Ashwin Vishwanath, who are at MIT and Harvard respectively, back in 2015, to kind of try and understand Sun's conjecture and see if they could prove Sun's conjecture. And it was a very confusing thing because we understood what particle vortex duality was, the bosonic particle vortex duality, but the fermionic theory didn't make sense for, the fermionic version of it didn't make sense for a number of reasons that had to do with silly things like factors of 2 and things like that. But it turns out that these factors of 2 were actually quite deep. The factor of 2 in the definition of the level number of the Chern-Simons gauge field, they're quite deep and they contain some really beautiful physics. And so we were trying to understand it in a way that was closer to the condensed matter. So we were trying to understand it from the point of view of how this could be used to understand topological insulators and topological superconductors. And so, for about a year, we spent thinking about this problem and we more or less had it figured out. And I was on my way to Princeton at the Institute for Advanced Study to spend a year on sabbatical there, when we learned that actually 2 other groups had figured it out as well, and approaching it from different directions. And those 2 other groups were rather famous, and we had very little hope of kind of catching up to them, but they very thankfully waited for us for a couple of days, and we all released this work back to back. And they were Seiberg and Senthil and Wang and Witten was one group, which was a Harvard-Princeton collaboration, and then Andreas Koch and David Tong were a University of Washington, University of Cambridge collaboration. So there were 3 papers together that were released on the same day. That was the Seiberg, Senthil, Wang, and Witten paper, and the Koch and Tong paper, and my paper with Horazio Nastasi. And they all kind of converged on the same idea at pretty much the same time, and independently as well. And so, the summer of 2016 was this beautiful time for these ideas, because we were able to show 3 different groups working independently, approaching the problem from different ways altogether, that there was this marvelous web of 3-dimensional dualities. So this had to do with low-dimensional, low-energy quantum field theory, and that there was this set of ideas that connected all of these theories together in a remarkable and beautiful way. And since then, since 2016, there's been a lot more results that have been arrived at. Much too much to mention in this talk, so I'll just pick a couple of them for different reasons. The first is that Shamit Kachru and his collaborators, pretty soon after the work, I think some circa October maybe of 2016, were able to show that you can derive this 3-dimensional web of non-supersymmetric dualities from a supersymmetric kind of master theory and a master duality. And that master duality is what we call 3-dimensional mirror symmetry, which relates a free chiral superfield to a supersymmetric 3-dimensional version of quantum electrodynamics. Again, the definitions of these things are details that you don't need to be concerned about. There's lots of papers, there's lots of reviews on the topic by now, and if anybody's interested, I can point them to them. The second remarkable development came from Nathan Seiberg and his collaborators, roughly from Princeton, but also from Italy, from CISA, as well as other institutions. And this was the extension of this abelian duality web between non-abelian duality web, which is a much harder thing to do. In fact, one of the directions that we approached this problem from was to try and give a fully non-abelian version of particle vortex duality, which we wrote down a couple of years before this Duality Web in 2014. And the upshot being that it's a really difficult problem. And Seiberg and his collaborators were actually able to extend the full abelian web to non-abelian duality web, which is a absolutely remarkable feat. And then the third point I'd like to make has to do with, if you want a kind of dimensional reduction from 3 dimensions to 2 dimensions, so one space, one time, that was written down by Koch and Tong and David Tong's student Carl Turner. And Koch, Tong, and Turner actually did a great service for the community in the sense that for a long time already, there were these dualities that were known in 2 dimensions, in 1 + 1 dimensions, one of which I've already mentioned, the massive Thirring model Assign-Gordon duality. So for a long time, there were these dualities that already existed in 2 dimensions. And if you knew the literature enough, then you knew there must be some kind of connection between all of these things. There were a bunch of different disparate dualities. So maybe they were connected in some way. But nobody quite put their finger on it until Karch, Tong, and Turner came along and were able to connect these dots and derive a two-dimensional version of the duality web that they were able to show followed from the three-dimensional web, essentially by dimensional reduction. So this is a beautiful story. You have this three-dimensional duality web, and three-dimensionals is special because there's this Chern-Simons stuff that's happening there that doesn't happen in even space-time dimensions. And you were able to do a dimensional reduction or dimensional truncation in some cases, and flow from the three-dimensional theory to the two-dimensional theory. And lo and behold, all the stuff that gets connected in the two-dimensional theory is stuff that you already knew about. You already knew that, massive Turing model, the dual to Sine-Gordon, that there were these dualities that had to do with the two-dimensional Ising model that go by the name of the Kramers-Vanier dualities. And suddenly they all kind of fell into place. So you had this beautiful puzzle, this multi-dimensional puzzle so far. 3 dimensions, 2 dimensions, and all the pieces kind of seem to just miraculously fit in a really beautiful way. And so, being physicists, we always like to push our luck and see what we can get for free. And so it makes sense to ask the question, is there a similar duality web in 4 dimensions? And, I started off talking about Maxwell electrodynamics, and Maxwell electrodynamics takes place in 4 dimensions, and there's a duality I just showed you exists. And you can, of course, formulate it in a more rigorous way than I hand-waved earlier in the talk. And so it makes perfect sense to ask the question, is there a similar duality web in 4 dimensions? The next question is, why is this answer not obvious? Why, I was able to start off with 3 dimensions and it wasn't obvious, but once you write it down, it kind of seems natural that that's how it should work, and it shouldn't work any other way. And you had all these dimension 2 dualities that existed as well. Great. And even there, once you were able to show that they flowed from the 3-dimensional theory, it seemed natural, but that was the only way that it could be. So why is this not an obvious thing in 4 dimensions? In particular, why did nobody, 2016, why did nobody in the intervening 5 years or so manage to write down a 3-dimensional duality web? And the answer comes in a number of different directions. Well, the first is in D+1 dimensions in general, for general D. Bosonization maps a massive Dirac fermion to a D-2 form field. So a D-2 form is a dimension D-2 P form, if you want, where D-2 is the rank of the form. And this thing is coupled to a scalar with some derivative interactions. And the boson, the bosonized theory, the resulting bosonic theory, has many nice features. In particular, it's gauge invariant. So if I change the field B, this D-2 form field, by some exact form, d omega, where omega is a D-3 form field, then the theory is invariant. And this is the phenomenon of gauge invariance, and we want our theories to be gauge invariant. However, and this was also something that was known for a while now, if the dimension of the space-time is bigger than or equal to 4 dimensions, then the resulting bosonic theory is actually a non-local theory, in the sense that there are, in essence, an infinite number of higher derivatives than just a quadratic derivative. So, for example, in 4-dimensional spacetime, a massive Dirac fermion, psi, say, gets mapped to a bosonic field, call it curly phi, and the kinetic term there actually goes like the Green's function 1 over box being the D'Alembert. So phi box 1 over box phi. That 1 over box is a non-local interaction. It's the Green's function for the theory, which is defined by an integral, and hence it's non-local. And then there's some coupling with some gauge field, but that's not really the problem. The problem is this non-local box inverse term. So we've identified the question we would like to ask. Can we write down a 4-dimensional duality web? We've identified a problem with naively writing this down, which is that the interactions become non-local and therefore problematic if I want to define a non-local unitary quantum field theory. And that sets the stage for what we want to do. So much of the manipulation in this theory comes from essentially being inherited from the 3-dimensional case. So it will make sense to review then what I meant by constructing this 3-dimensional duality web. So far, I've just been talking in vagaries. So let me be a little bit more specific now, and I'll show you exactly how or exactly why we think various theories are dual to each other. Just looking at the time, I don't think I'm going to have a chance to go through the details of the 4-dimensional construction, but it doesn't really matter because much of the heavy lifting, much of the hard work actually takes place in 3 dimensions. So let's start off by establishing some notation. So my notation for scalar is going to be phi. For fermions will be psi or some variant thereof. An external gauge field will be denoted by a capital A, a dynamical internal to the theory gauge field, something that actually evolves with the theory, will be denoted by a lowercase a or lowercase b, as the case may be. And I couple things together through a covariant derivative, and the covariant derivative term is like d minus IA. Pretam, I noticed you've just popped up on my screen. Is there?
No.
Am I running short of time, or?
No. It's okay.
How much time do I have? I see I've been talking for 40.
There is about 15 minutes, more than 15 minutes.
Okay, good. Okay, so I'm just going to go as far as I go, and then we'll take questions. And if if people have questions that relate to the high dimensional stuff, then I'll address it there. Okay. Okay, so the physics, of course, is contained in the actions for the theory, because from the actions I write down the path integral or the partition function, and that's where all the manipulations take place. And the goal here is to establish relationships between theories and not so much write down equations of motion and solve those equations of motion as differential equations. That's not the name of the game here. So I should tell you about some of the actions that we'll be talking about. The first one is if I have a massive scalar. So if I just have a massive scalar coupled to an external gauge field, then the action looks like the action is an action functional of the scalar phi and the gauge field capital A. It's an external gauge field, so it doesn't have any dynamics of its own. So you won't find a Maxwell term or a Chern-Simons term involved here. The kinetic term looks like d phi squared, mod d phi squared, because these are complex scalars. They're charged scalars. What this means is it's shorthand for d mu phi, d mu phi. The mass term, of course, enters like minus m squared mod phi squared. And then sometimes I would like to turn on some self-interaction, so some potential term. And the potential term will go like lambda mod phi to the 4. Again, we're talking about a complex scalar here because it carries some charge under the gauge field, which is what tells me that it couples to the gauge field. Otherwise, it's just floating around and the gauge field is in the background and we don't care. The second action that we care about is the gapped fermion coupled to an external gauge field. In this case, a gapped fermion is really what I mean by a massive fermion. So it has a standard Dirac action, I psi bar d psi. But then I also have a I m psi bar psi term. So again, it's quadratic in the field. Whenever I see something that's quadratic in the field in the action, I know that that's the mass term. So there's a mass term here, and it's that mass term that gaps the spectrum of the theory. Then I'm going to need a Chern-Simons term, and the Chern-Simons term is a term that only occurs in odd dimensional spacetimes, and it's the integral of what's called a Chern-Simons form. And Chern-Simons form is a 3-form, which goes like A wedge dA. Now, there's some notational abuse here that's taking place, and I'm dropping all the wedge products. So these are forms in the differential geometry sense, which means that when I write down A, I really mean A mu dx mu, where dx mu is the basis for 1 forms in the theory, and A is then a 1 form. So if A is a 1 form, its exterior derivative is a 2 form, and so A wedge dA is a 3 form. And a 3 form gets integrated over a 3-dimensional space, or a 3-chain, and that gives me the integral. And the coefficient sitting outside of this kappa over 4 pi, the k over 4 pi, the k here is what's called the Chern-Simons level number. And this actually plays an important role in this story. And the fact that it's a k over 4 pi and not a k over 2 pi is one of the hints that at least Seiberg and his collaborators were pursuing in arriving at the story. There's a generalization of the Chern-Simons term that will also be important here called a BF coupling. And a BF coupling doesn't only have a gauge field A, it also has a gauge field B. And the BF coupling is, unlike the Chern-Simons coupling, which is an ADA term, the BF coupling is an ADB term. Again, B is a 1 form, so DB is a 2 form, so ADB is a 3 form, which I have to integrate over a 3-dimensional space. It doesn't carry a k in front of it, so it's just a 1 over 2 pi integral ADB. And you can see by doing integration by parts that the BF action functional of AB is equal to the BF action functional where I switch the A and the B around. But as you would expect, if I do integration by parts, it also picks up a boundary term. And this boundary term in a manifold with a boundary is actually quite important. But in a manifold without a boundary, which is largely what we're going to be talking about here, it doesn't play any role. So we typically drop the boundary term and we say that this SPF is symmetric in its arguments A and B. The final idea here is the one that actually transmutes a fermion into a boson. And the statement here is that if I take a fermion and I attach a flux quantum, so basically if you want to think about it, I put these fermions on the plane, and then I crank up some magnetic fields perpendicular to the plane. Where there's a bundle of magnetic field lines, that's a flux. The fermion couples to that flux, and the fermion plus the flux actually behaves like a boson. And in fact, this statement holds in reverse as well. A boson coupled to a flux quantum behaves like a fermion. So the thing that's actually doing the statistical transmutation here is this flux attachment story. And it's a really important part of this story. And when I say that 2 theories are dual, and in particular, when I say 2 theories are low energy dual, I will mean that their partition functions for theory A and theory B are equal to each other. So if I write down the path integral or partition function for theory A, and I can manipulate it to show that it gives me another partition function for, let's say, theory B, then I'll say that these 2 theories are dual to each other. So how do I establish this, ZA equal to ZB story? This actually goes back to some beautiful work by Cliff Burgess and Fernando Quevedo, where in trying to understand these dualities, they actually wrote down an algorithm to dualize these theories. And the algorithm goes as follows. So suppose I start from theory A. So I have its partition function ZA, and it's got some global symmetry. And we're going to assume that all the symmetries here are abelian, so some global U1 symmetry. Then I gauge that symmetry. So what that means is making that symmetry local, and it requires adding in a gauge field. And that gauge field has to be a dynamical gauge field, so I need to introduce some kinetic term for it. Okay. And in 3 dimensions, I have 2 options of kinetic terms, unlike in 4 dimensions where there's only 1. In 3 dimensions, I have the Maxwell term, so something that goes like F squared, where F is the field strength tensor, or the Maxwell tensor, associated to the gauge field A. But I also have this Chern-Simons term, this ADA term. Okay, so this is going to be important, and I'll tell you why the Maxwell term actually doesn't really matter in the story. So I introduce a dynamical gauge field that gauges this global symmetry. And then what I do is I want to make sure that I'm not actually adding any new degrees of freedom to the theory. In other words, I need to make sure that this gauge field that I introduce, this little a, is a pure gauge field. And a pure gauge field is one where the Maxwell tensor, this Maxwell tensor, this f equal to dA, the exterior derivative of A, vanishes. So if that's true, then it enforces some constraint on this theory, which means that the theory is pure gauge, which means I haven't actually introduced any new degrees of freedom into the theory. Okay, so step one, gauge the local symmetry, gauge the global symmetry and introduce a gauge field, dynamical gauge field. Step two, make that dynamical gauge field pure gauge. It's kind of trivial. Step three is, how do you actually enforce that? Well, you enforce it the way you enforce constraints in an integral in general, from what you were learning in first year already, which is by a Lagrange multiplier. In this case, the Lagrange multiplier I'll call lambda f. So I add some lambda f term to the action, and that produces a new action, which is actually this master action that I kind of hinted about a little ways back. And the master action then is an action functional of phi, my original field, A, the dynamic gauge field that I introduced, and this Lagrange multiplier, which I'm now going to think of as an actual field by itself, not just a constraint enforcing lambda. Okay, I'm going to think about it as an actual field. So now I have two options. If I integrate out lambda from this integral, so if I do the integral over lambda, right, then I end up back in theory A, which was just a theory of phi, and the original theory that we started off with. On the other hand, sorry, my bad. Let's go back a little bit. If I integrate out lambda first, and then A, the gauge field, I end up with my original theory, theory A, which was a theory of just phi. On the other hand, if I integrate out first A and then phi, I end up with a new theory. And this new theory has a dynamical variable lambda. The thing that we were just calling the Lagrange multiplier is now promoted to an actual dynamical field, and I have an actual dynamical field theory of lambda. And this is theory B. So these two things are dual to each other. And they're dual to each other in the way that I just described, which is that their partition functions are equal. That means that they have a low energy duality. So when these steps 1, 2, 3, and 4 are possible, we will call theory A and theory B dual to each other. And the way we'll denote it is we'll say that the Lagrangian of A is dual to the Lagrangian of B, and we'll denote the duality by a double arrow. So whenever I write down these double arrows, that's all the stuff that's going into it in the background. Okay, so it's not just I look at it and I write down some arrows. No, you actually have to check all steps 1 through 4. So let me do some examples. The first one is bosonization, which is a Bose-Fermi duality. And this is the statement that the partition function for the Z fermion that I wrote a couple slides ago, with gauge field capital A, background gauge field capital A, multiplied by e to the minus I over 2 Chern-Simons action. So all of these actions are defined back here. There's S fermion. So Z fermion would be the integral of S fermion of e to the I S fermion with respect to psi, so that gives me Z fermion of A. And here's the Chern-Simons action, and there's the BF coupling. So just keep these in mind when I'm talking about them going forward. So on the left-hand side here in the first equation is a fermionic theory. On the right-hand side is a scalar theory plus flux. So the scalar theory plus flux here is this action that looks like this. It's got S scalar, the scalar action, plus the Chern-Simons action for the field little a, plus this BF action that couples little a, the dynamical gauge field, to the external gauge field, something like an external magnetic field sitting in the background. So there are a couple of things to note about this duality. One is, the obvious one is that on the left-hand side is a theory of fermions. On the right-hand side is a theory of bosons. And what's happened here is a statistical transmutation in the sense that fermions obey Fermi-Dirac statistics. Bosons obey Bose-Einstein statistics, right? So normally the two don't talk to each other, they don't mix. Well, I've demonstrated here that at least at low energies, they're describing the same physics. Okay. The second thing that you would note here is that nowhere in this action is a Maxwell term, something that goes like 1/4 E², where E is the charge of the scalar, dA meaning F, the Maxwell tensor. And that's because in the low energy limit, where E goes to infinity, this term goes to 0. So the Maxwell dynamics actually don't contribute anything. This is why we will always just talk about the Chern-Simons or the BF actions. The second thing to note is that if I act with an operator in the quantum theory, if I act with an operator that reverses time, so this operator t hat takes anywhere you see t in this system, for example, in the integral for the action, you replace it with minus t. Well, if you do that, you actually get another version of this duality that says that a fermion coupled to e to the plus I/2, notice the minus in the top line and the plus in the bottom line, S Chern-Simons, is equal to this Z tilde of a scalar plus a flux, where the Z tilde is the same as Z, except the Chern-Simons term gets a minus sign and the BF coupling gets a minus sign. This actually makes all the difference in the world. Why? Because I can then use this Bose-Fermi duality, something that's well known and relatively well understood, to establish new dualities. In this case, the new duality that we'll establish is the Fermi-Fermi duality. So the last one was a Bose-Fermi duality. This is a Fermi-Fermi duality, a duality that relates to fermionic theories. So, and in some sense, this actually establishes Sun's conjecture that the composite fermion is, in fact, a Dirac fermion written in a particular way. So in words, this duality says that a massless Dirac fermion coupled to an external U1 gauge field, capital A, is dual to this composite fermion chi, which is coupled to two gauge fields. One is an external gauge field, capital A, and the other one is a dynamical U1 gauge field, little a. In equations, the statement here is that this Z fermion coupled to an external gauge field, free fermion coupled to an external gauge field, is dual to three-dimensional quantum electrodynamics, ZQED3, which is this path integral, which contains a fermion action and a BF action that couples little a with capital A. Okay? And in fact, so that's just a statement of Sun's conjecture, the Fermi-Fermi duality. Now, given that we know how to write the Bose-Fermi duality in this path integral way, we have all the tools we need to derive the Fermi-Fermi duality from 3D Bose-Fermi duality. And it goes like this. Step one, you start from the bosonization duality. You take your external gauge field, this thing that I said was just lying, chilling out in the background, not really doing anything, some external magnetic field that somebody turned on, but your electrons live on the plane and they experience this external gauge field. But now you promote it to a fully dynamical gauge field, which we'll call little a. And then you turn on a new background field, a new external gauge field, which I'm going to call capital A. I know its notation is confusing, but it's consistent with the literature. So the thing to note is, if I go back to my Bose-Fermi duality, when I do this, the left-hand side just becomes the partition function, the path integral for QED3. The right-hand side, on the other hand, becomes the partition function for the scalar field coupled to a flux. Right? It's not quite where I want to be, right? Because I want to go from Fermi to Fermi. Well, what I can do is I can integrate out the dynamical gauge field little a by using its equation of motion. Some technical details here that I don't really need you to focus on, but the point is that I integrate out this dynamical gauge field little a, in which case the right-hand side becomes this weird, horrible expression here, but I've seen this horrible expression. In fact, that horrible expression is basically what happened when I acted with the time reversal operator on the original duality. So I can use it to cancel out the additional exponential pieces. So I have one piece that looks like e to the minus I over 2 S Chern-Simons multiplied by e to the plus I over 2 S Chern-Simons times Z fermion. Once the exponential pieces go away, I'm left with Z fermion. In other words, I've shown that ZQED is equal to Z fermion, and that was my claim, was that whenever I could do this, I could claim that the two theories were dual to each other in the low energy sense. And then finally, I can use it to, I can use the combination of these two to derive a Bose-Bose duality, right? And this is the final thread in this three-dimensional duality web. And basically, it goes in pretty much the same way. I start off with the bosonization duality that relates fermion plus flux to a scalar. I promote the external gauge field, in this case C, to A, and then I couple in a new external gauge field, which I'm going to call A, capital A. Then the right-hand side becomes basically the right-hand side of the first equation in this slide becomes the scalar plus flux quantum. And the left-hand side becomes the time-reversed statement of the fermion plus flux multiplied by this e to the plus Chern-Simons. And then, of course, I have to substitute back into this equation. And when I do that, I'm applying the bosonization twice. And when I apply the bosonization twice, I find precisely what I want. That scalar QED, so this is quantum electrodynamics, but not with a fermion, with a scalar field, is dual to just a Wilson-Fischer scalar. In fact, it doesn't have to be dual to a Wilson-Fischer scalar. It could be a free scalar or Wilson-Fischer scalar. The duality doesn't actually, the bosonization duality doesn't actually disambiguate between those two. The second point to note is that implicit in this argument is the fact that there are no boundaries. And a little more deeper than that, there are no holonomies. There are no holes in my space-time that doesn't allow me to contract points. So this is an important point if I want to, for example, think about what happens in finite temperature field theories. So there I will have a thermal circle, and a thermal circle does have holonomies, which means that I can't just throw away the boundary terms. And where this manifests is precisely in this step 3 of integrating over A by using its equation of motion. Okay, so everything that I've said so far assumes that there are no holonomies in the gauge field, which means that all the arguments that we made are perfectly valid. And if I play the same game with more dualities, if I play the same game with other fields, I can generate more dualities. For example, I can show that QED3 with two flavors of fermions are self-dual. I can show that a scalar plus a level 2 Chern-Simons gauge field is dual to a fermion plus a level 3 half Chern-Simons gauge field, etc., etc. There's many games you can play. There are many more dualities you can generate. Many of them have been generated already. It's not clear that we've exhausted all of the relationships between these theories on the plane. But what is clear is that there's a beautiful set of ideas, mathematical ideas that underpin these things that we're just learning about now, even though these theories have been around for decades. So let me give you a small hint in the, let's say, 1 minute I'll take extra about the four-dimensional construction. So to understand the four-dimensional construction, if I'm trying to build a four-dimensional version of the story, I need to say something about theta terms in electrodynamics. So let's tell you a little bit about electrodynamics in 4 dimensions. So it turns out that if you didn't know anything about all of this quantum field theory stuff, and you were a very naive first-year student, say, and you wanted to write down the action for electrodynamics in 4 dimensions, if you demand that theory be A, linear, B, Lorentz invariant, in other words, relativistic, and C, gauge invariant, then there's only one action you can write down, and that's the Maxwell action, which looks like the familiar form F mu nu, which is basically E squared minus B squared. And if I vary this action with respect to A mu, then I get Maxwell's equations, and we all know about this. It's things we learned in first year already. However, there's another story at play here, which is that in 4 dimensions, a 2 form, which is a rank 2 object that carries 2 Lorentz indices like this F mu nu, is dual to another 2 form. And that's because in D dimensions, a P form is dual to a D minus P form. This is some simple combinatorics that you can work out. And once you learn about differential geometry, you learn about Hodge duality. So this is a duality called Hodge duality. It's well known from differential geometry. And it so happens that in 4 dimensions, 4 minus 2 is 2. So a 2 form is dual to a 2 form, which is not true in other dimensions. Well, what this means is that I can start off with F mu nu, the Maxwell tensor, or Faraday tensor, sorry, and I can dualize it by multiplying it with this epsilon mu nu lambda sigma, which is a completely antisymmetric tensor, which means that if I interchange any two indices, mu or nu, lambda or sigma, mu or lambda, nu or sigma, then it picks up a minus sign. And the resulting object, star F mu nu, is what we would call the dual Faraday tensor. And that's just a fancy way of saying, take the electric and magnetic fields of the one theory and replace them with the magnetic and minus the electric fields of the other theory. Well, the result is that I can define a new term in the story called the theta term, which instead of F mu nu is really star F mu nu. Right, so it looks just like the Maxwell term, except that instead of having the Faraday tensor for both components, I have one the Faraday tensor and the other one the dual Faraday tensor. And the resulting theory, if I write it in terms of the electric and magnetic field, is not E squared minus B squared or anything like that. It's E dot B. Well, that's generally a term that you would discard because you would say, it's a topological term, and I can write it as a total derivative, and I can always get rid of it. But it turns out that it actually has some important consequences, and those consequences are borne out by this theta term. Right, so the theta term itself has no dynamics, and it's a topological term because I can always write it as an exterior, as a total derivative. And as you know from first year already, by the fundamental theorem of calculus, the integral of a derivative vanishes. But it actually turns out that this theta term is pretty crucial in some physics problems. The first such physics problem is in the idea of axions, in which this theta coefficient in this action is promoted to an actual dynamical field. It has dynamics of its own, and it's a function of space-time variables. And this gives rise to a set of particles that high-energy physicists or cosmologists call axions. The second important physical problem that these theta terms manifest in is in the idea of topological insulators, which, as I said earlier, is a novel type of quantum matter that's characterized by theta equal to precisely pi. And this should be compared with the vacuum state where theta is equal to 0. So our approach to building a full 4-dimensional duality web, which we did in our paper of March last year, builds on using the Burgess-Quevedo prescription in 4-dimension. So we start off with 4-dimensional bosonization as a seed, in the same way that I motivated starting with a 3-dimensional bosonization as a seed in the previous slide. Okay, and I think I'm going to stop here. The story gets a little bit more complicated at this point, but I see I'm already 10 minutes over time. So let me stop here, and I'll take some questions that are relevant to the talk.
Okay, sir. Thank you for your wonderful presentation. So we have got few questions in our comment section. So if you allow, we can start our discussion session. The first question: will string theory finally be put to the experimental test in near future?
Okay, so it's not really relevant to the talk, but I'll try and answer it in any event. I don't know. I don't know whether string theory will be put to an experimental test in the near future. I don't know whether any theory of quantum gravity will be put to the test in the near future. This is a statement about very, very high energies, and we have to be very, very smart about the questions we want to ask and where we want to ask it in order to be able to address that particular question. But what we are learning is some of the tools that we learn from string theory, like dualities, like S-dualities and things like that. These are tools that are entirely applicable in low dimensions where we can access these things. So the physics that I was talking about today is really not physics about string theory. It's physics about it's physics of topological insulators and topological superconductors. These are actual things that you can make in a lab. Are we testing string theory? I don't think so. Are we testing ideas from string theory? Very much so.
So thank you. So we have another question. So do gravitons exist?
Well, it depends what you mean by gravitons, and it depends what you mean by exist. The only word I agree with there is do. So what do I mean by gravitons? Well, we know that gravitational waves exist, and we know that other forms of waves exist, and typically where we find these other forms of waves, when you quantize those waves, the particle excitations are precisely the, for example, you quantize the electromagnetic wave and you get photons. And so if you connect the dots, then it seems natural that gravitons do exist. Can we probe that gravitons do exist? Is there an experiment that's analogous to the photoelectric effect that will conclusively prove that gravitons exist? Again, I think that gravitational interaction is so weak relative to the other interactions, and the energy scales that we're talking about are so high compared to the other interactions that certainly not in my lifetime do I expect that we will conclusively prove that gravitons exist. Do I believe that they exist? I do. That's because I believe the math.
Thank you. We have another question. So can string theory unify all the fundamental forces and explain the dark matter also?
Okay, so these are two separate statements, right? The one is, can it explain dark matter, and can it unify the fundamental forces? So can it unify the fundamental forces? Yeah, I don't know. I think it's one of these strange things that it's been around for like 50, 60 years now, and we're still like children, learning about it. If you give a child an iPad, for example, then they very quickly learn to become very adept at doing things with it. My children are certainly better than me at using the iPad in many ways. But do they understand how it works? No. Do they understand why when you move your finger on it, it does what it does? Do they understand why if you put a glove on and you move your finger on it, it doesn't do anything? No. So we're like children with the iPad. We can do various things with it, and it's all pretty, and we think we understand why it works. But really, there's deep underlying physics here that we don't understand, and this is a really remarkable thing. And I mean, you can see, my work in the area has kind of shifted back to quantum field theory. And one of the things that I think few people appreciate is that the leaders in the field, the people that we look to for guidance as to where the field is going, the Maldacenians, the Wittens, the Seibergs, they're all spectacular quantum field theorists. So the real deal here is quantum field theory. And for a lot of people, myself included, string theory is kind of a high energy version of quantum field theory. It's what we call an ultraviolet completion of quantum field theory. If you try to probe quantum field theory at very, very high energies, then the structure of quantum field theory breaks down, and you have to replace it with something that's adept at higher energies. And that thing that's adept at higher energies looks to us to be string theory. I'm not claiming that it's unique. I'm not claiming that string theory unifies all the fundamental forces. I can tell you, why we think it should, but what I am claiming is that it's a very, very good candidate for the ultraviolet completion of quantum field theory. And really, the edifice, that the foundation that everything's built on here, is quantum field theory. So I used to teach an undergraduate course in string theory, because back in the day, I believe that if you taught it appropriately, then you could introduce it to an undergraduate audience. Today, I believe that particular direction does a disservice to my students, and so I'd rather focus on teaching them quantum field theory and then let them learn the high energy version as they need it, but really get the foundations going. So why would we think that string theory unifies all the fundamental interactions? Well, one of the things that we've learned, again, from quantum field theory, and if you want an exposition of this, really, Steven Weinberg's books are the best place to go looking for it, is that as you crank up energies, fundamental interactions couple together. So you start off with, at the low energy scales, you've got electromagnetism, weak nuclear, strong nuclear, gravity. And then you turn up the energies. And what you find is that you get running of couplings, and basically the electromagnetism merges with the weak nuclear interaction, and then you get the electroweak theory. And you keep going at high energies, and then strong nuclear interactions eventually meet up, and you get grand unified theories, right? And of course, the outlier here is gravity, which you have to really crank up the energies very, very high to have gravity merge. But what we seem to learn is that at the scales where we expect gravity to become a quantum theory, to be described by a quantum theory, where gravitons should play a role, all the other interactions, strong nuclear, weak nuclear, electromagnetic, are already strongly coupled to each other and already very, very quantum. So if you want to describe a theory of quantum gravity, you can't just talk about gravity. There's no decoupling regime where you can turn off all the other forces, just focus on gravity, and get a consistent answer. You could certainly do it. You could try to do it, but I don't believe that the resulting theory is consistent, because at some point you have to turn on the additional forces, and they have to couple, and they're very nonlinear, and they're very quantum, and you have to learn how to deal with those nonlinearities. And one of the things that drew me into string theory in the first place is that in string theory, you're kind of forced to do this. You have no choice. You can't turn off other interactions and just focus on gravity. You're forced to think about everything all at once, or nothing at all. So that's the, can it unify all the four fundamental forces? I don't believe, well, okay, so I don't know if it can, but if it's going to be a consistent theory, then it has to. It has no choice. Point one. Can it explain dark matter? I think you might have meant dark energy instead of dark matter. Dark matter is something that we believe exists on macroscopic scales. And here, I don't believe that string theory per se ought to be able to explain dark matter. I'm sure you could cook up some very Baroque kind of theory that might be able to do it, but I would be hard-pressed to believe that theory. I don't believe that string theory by itself directly ought to be able to explain dark matter. Dark matter is macroscopic. String theory is microscopic. And I'm a strong believer in effective field theories, and that I don't think that string theory ought to describe dark matter any more than I think that string theory ought to describe how my car works. Newtonian mechanics works perfectly fine there, because Newtonian mechanics is the effective field theory that describes the physics on these scales.
Okay, sir. Thank you. We have another question. So if we want to represent an electromagnetic wave in 4D, then what would be the fourth component for extra dimension?
I'm not sure what you mean. We live in 4D. The electromagnetic waves that we describe in electrodynamics is waves, plane waves in 4D. They look like e to the I E times t minus p times x. Those are the additional component would be energy times time.
Okay, this may be the last question, sir. So please suggest me some books on differential geometry as a basic learner. I'm a student of physics and interested in general relativity and theoretical physics, and also quantum field theory.
Okay, you're in luck. I have 2 books right here that I happen to be reading at the same time that I quite like. So the differential geometry book you should look at is Gauge Fields, Knots, and Gravity by John Byers and Javier Munain. It's wonderful book. It's not very let's say mathematically rigorous, but it's written in a beautiful way that is rigorous enough. And the ideas are very, very clear. So Gauge Fields, Knots, and Gravity. It's one that I started reading as a graduate student, and it's one that, whenever I want to learn new stuff about things or refresh my memory, I go to that book, even though there's many other books that are far more detailed and far more rigorous and far more tied to physics. So, for example, Nakahara is another one that I'm working through right now. But if you're a first-time learner of differential geometry, Byers and Munain is a great one. Quantum field theory. This is a unconventional choice, but I would recommend Shankar's Quantum Field Theory and Condensed Matter. So this is by Ramamurthy Shankar, who's at Yale, and he has a very famous quantum mechanics book called Principles of Quantum Mechanics. Get that book too. It's also a brilliant book. But this is a new book of Shankar, Quantum Field Theory and Condensed Matter. It's also very, very nice to read, worth getting. And then finally, if you want to set up lecture notes, I cannot recommend them highly enough. They are beautiful, beautiful set of notes. They're all free. They're all on his website. Go to David Tong's website. So that's TONG, and just download all his notes and just read them. It'll keep you busy for the next couple of years, but you will learn a lot in the process.
Thank you. Thank you for your wonderful presentation and nice discussion session, sir. It's a great opportunity for the viewers and the student to learn these things. So I think everybody enjoy it. So thanks again. And I'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation, sir.
It's been a pleasure.
Yeah.
Thank you. Bye-bye.